So hello everyone, welcome to lecture 9 on finite element method. So in this lecture, we want to switch gears a little. And as I mentioned before, this lecture has basically 3 parts. The first part was understanding finite element method via string combinations. And we have done that. So the string combination part, we already are done with. So you won't see those springs anymore. But then again, I emphasize that you should not underestimate the importance of that, because by doing that, we learned about nodes, we learned about elements, and then again, how you would list them, basically the node list, element list, and then how you do well, let's say what we call the extended node list, and then we learned also how to compute stiffness and proceed with the assembly. So this is what we have done so far. So the key ingredients of the finite element method we have already touched upon using springs combination, but now we want to go sort of backward, and then we want to formulate one-dimensional finite element method. Now, why we are doing this? Remember, I told you that the finite element method itself is just a method to solve differential equations, and it is essentially invented by mathematicians almost 40 years before it was adopted by engineers. So it's a mathematical technique. Now, what we did with the springs and the spring combination, it was nice, but you can imagine that you understand that, or you feel comfortable with those as an engineer. So if I draw something like this and I tell you, well, F equals kx, you don't feel alien to these notations. This feels pretty familiar to you. And also, more importantly, you can connect this to what we call as I mentioned, the truss structure. And you would say, well, the stiffness of a spring looks like EA over L, and now that E is elastic modulus, which again you are comfortable with. So let's say from a mathematical perspective, if you want to formulate that, we need to start from let's say a differential equation perspective, and that's what we want to do. So before we do that, I write sort of a road, or I draw a roadmap here, which we will follow in the next few lectures, and we will work on this map together a little more. So the first thing we want to do is the so-called strong form. Okay, so these are sort of the cornerstones or the milestones that we need to pass to understand and to formulate a finite elements method. So the first thing we want to do is the strong form, and we need to understand what that means. After that, we would go to, let's say, weak form. Okay, so these are more like stations, and basically what you would do in between is how you do that. So we need to learn how to go from strong to weak form. Again, right now you don't know exactly what is a strong form, what is weak form, and obviously you don't know how to go in between. But sooner or later we will learn these things, and also we learn the path in between. So again, these are more like stations, and this would be like a path between the two. We want to go through this map together. And after that, after, let's say, establishing the weak form, we want to do this other thing that we would call approximate form. So obviously, then the road is some road that takes us, let's say, from weak to approximate form. Okay. So let me just clean this and write them in the same letters. Okay. In between, so between weak and approximate form, there is this thing that is more like a discretization process. Okay. So basically what we do is not exactly going from weak to approximate form. We go from, let's say, a weak form to a discretized form, and then we go from a discretized form to approximate form. So this thing itself is, if you want, it has also two steps. So if you want, there is this intermediate step or station, again, maybe we call it discretized form. So basically what you need to do is first to go from weak to discretized form, and then from discretized form to approximate form. Okay, so there is sort of an intermediate station there, and then obviously when you want to do this and when you want to talk about this approximate form, we would have to discuss this so-called approximation techniques. Okay, so these are tools that we need to have, let's say, in order to go through this journey together. So we need to have or to learn what the approximation techniques are. And in particular here, we use something that we later identify as shape function. Okay. And then there is, let's say you have your approximation, your approximate form, and you know your approximation techniques. Now, the last thing you need to know or you need to do is to evaluate. Okay, let's say it's not a form anymore, it's a numerical evaluation. Or maybe you would like to call it numerical integration. Okay, so we would end up with some integrals that we would like to evaluate numerically, so that there is that. But the path in between is actually interesting because it's now a quite different thing. In order to do that, we do this thing that we say, let's say we go from physical to natural space. Okay. Maybe I actually take this as an intermediate station by itself, and yeah, think of it as an intermediate step by itself. I try to draw also a sort of ellipse around it if it works. Good. So this is basically how it works. In order to do that, you basically need to go through a let's say a space change, a space transformation. All right. Okay, so what you see here in this picture, again, possibly everything you see is the first time you see it. They are all completely alien to you. But we call this, let's say, roadmap for the next few lectures, but it's really the roadmap for FEM, if you want. For us, it's just the next few lectures. And it turns out that it doesn't matter if it is 1D or 2D. And that's why I like this generic form. So it would be first for us for the one-dimensional finite element, we go through this. But as I mentioned, almost in the next 8 lectures, give or take, in the next 8 lectures, we will see this map, and then we go through each of these little stations one by one, and eventually you would have something which looks like a one-dimensional finite element method. And the thing you would have at the end looks like a one-dimensional finite element method formulation, in a sense that a mathematician would understand. You don't need to, let's say, explain it or understand it using springs or make a similarity between the springs. It would be a differential equation. In other words, the first step, the first thing that we start from and we call a strong form is indeed a differential equation by itself. So what we call a strong form is indeed a differential equation. And then we want to solve that differential equation. And let's say what you would have at the end is the solution. Well, it's approximate solution. Obviously, approximate solution to differential equation. So let's say if that differential equation is called star, here we want to find an approximate solution for the star. That's what we want to do. All right, so that is a very important roadmap for us, and I need you, or I want you to remember this again. As I mentioned, for the next possibly 8 lectures, I will show this roadmap at the beginning of each lecture, and I tell you where we are, and we kind of locate ourselves in this map. And now we can basically start the journey if you want. So, do you have any question? So what I want to do now is to tell you something about the finite element method by itself, or the way we are gonna do it. So it's a brutal simplification. It's not very scientific the way I'm going to explain it, but I think it's a good way to start. So let's say understanding finite element method. Maybe I would just say via an analogy. And then again, I emphasize it's just a brutal simplification of, let's say, almost 80 years of science. So it's obviously a lot more than what I'm going to say here, but I think for the scope of the course, this example would do the job. Let's think about sinus of 45 degree. So if we think about the sinus of 45 degree, and we want to evaluate this, what can we do? How many different ways do we have to do this? Let's say the first thing is you can just pick up your calculator and then, I don't know, you calculate it, or any other different techniques that you know. Okay, I'm going to just call it calculator for now. And if you do that, you would see something which looks like this. Okay, and then at some point you have to basically cut the digits, right? I mean, you cannot write these digits forever. At some point you cut it. So this is an approximation. Okay, what we want to do here, or let's say the idea here, is to talk about approximation of, or different approximations of finite element method. Okay, so remember here we use the word approximate solution. So eventually we end up with an approximate solution. We want to know where we lose accuracy, where the approximation is. And then again, I'm going to just explain it via this simple example of sinus 45 degree. All right, so you see, if you do that, you can approximate solution. Does that make sense? So when you cut the digits at some point, you know the solution is more accurate, but you need to cut it to be pragmatic. And that is what we are going to do eventually. If you run a simulation with the finite element method, and if you don't have the biggest or the best supercomputer, even if you have, eventually you have to cut the solution at some point. Okay, that's the first type of approximation that is, let's say, inherent to finite element method, and we need to understand, and I will explain that shortly, and I will make the connection to the real finite element method soon. But now back to sinus 45 degree. Let's say we do a Taylor expansion. How about that? And if you don't remember the Taylor expansion of sinus, it says, let's say sinus x could be an angle, is sum over, let's say, n minus 1 to the power n minus 1, x to the power 2n minus 1 divided by, let's say, 2n minus 1 factorial. Okay, so that is your Taylor expansion. And then again, you can see the problem with the Taylor expansion, as we had before, is this infinity on top. And you can imagine again, even if you have the best computer, that infinity is problematic. At some point, you need to make a compromise. So let's say if I want to expand that Taylor expansion a little, it's going to be x minus x to the power 3 divided by 3 factorial plus, I don't know, x to the power 5 divided by 5 factorial, and so on. And then again, at some point, you have to cut the solution, okay? But in this case, what you cut is not the solution itself in terms of number. You actually are cutting the equation. So it is different from what you had before. So you may want to think of this one as approximate equation. Okay. So if you need to approximate sinus of 45 degree, you can make an approximation of the solution. You can make an approximation of the equation. And these are, as you can see, these are two different, or they have two different natures, at least in this brutal simplification we talk about. Now, remember, even if we do this, we still have that solution, that, let's say, solution approximation, even if we do the, let's say, the blue line, because let's say if I want to just evaluate what we have here, for instance, or proceed with the Taylor expansion, you would get something like this again. You can imagine this thing is also not very nice. At some point, you have to cut this too. So that's, let's say, that solution approximation is still here. Okay, let me just maybe change the color to be consistent with what we just had before. Okay, so eventually, if you do that, and then let's say you want to evaluate it, at some point you have to cut that too. And then you do exactly the same solution approximation as we did before. Okay, so approximating equation, it doesn't mean that you don't approximate the solution. You can approximate equation by itself or not, but still you may have to approximate the solution. So these are two different things. And then this is not even everything. There is a third type of approximation that you may have to also impose in your problem or to your problem. So what is that? What is the third type of approximation? The third type of approximation that we have here, and I draw it in green, is, okay, let's say we have, so far we have solution approximation, equation approximation. We can also have, let's say, input approximation. So what is the input here? The input here is the 45 degree. So what is 45 degree anyway? So 45 degree, if you think of it as, let's say, pi over 4 in radian, you can clearly see that also that number, although we just write it as simple 45, if you think of it as pi, this itself, it has something, right? I mean, it has some level of approximation. So in other words, what I'm trying to say is that even if you do the Taylor expansion, even if you do a very, very long expansion, and even if when you need to, evaluate them, you have a very good calculator and you can have many, many digits. Still, the input that you feed to that equation is pi over 4. And that pi over 4 itself, it is also an approximate number, okay? And then you have to do, again, that approximation. So let's say pi over 4 is, I don't know, 0.785398. 1634. So eventually, this is what comes to your Taylor expansion when you want to do that. So this is the third, let's say, third format of approximation. Okay. So we have three sources of approximation. I hope that's clear. Again, this is a, let's say, a brutal simplification, but I think it will do the job for now. So the first thing, as we said, it was, let's say, solution approximation. The second thing was equation approximation. And then eventually you have, let's say, input approximation. So these are the type of approximations that are inherent to also a finite element method. So approximations. So what I want to do now is to sort of identify these three approximations in a typical finite element problem and tell you where you can identify these if you have a finite element problem. Okay, so we start with approximating the solution. You can imagine that, again, you're using computers and you do integrations. And by the way, as I mentioned, we do numerical integrations. Okay, so here again, back to the picture we have this thing, numerical integration. Even if we do exact integration, we are not safe, because even if we do exact integration, eventually we are using computers, we are using numbers, and then you have to cut the digit at some point, as we did before. Okay, so I think this is fairly straightforward, that there is no way to use computers for any simulation, for any, let's say, solution, and avoid having solution approximations. Okay, so this is sort of inherent to computers, if you want, or inherent to numerical techniques, if you want. All right, now there is a famous sentence. Some of you may be familiar with the finite difference method, what we call FEM. There is a famous quote that finite difference method approximates only the solution, but finite element method also approximates the equation. Okay, so there is a fundamental difference in that sense. In finite element method, we are not solving the equation. We change the equation and then we solve it. And as I mentioned, even after we change the equation and we solve it, we still have to do the first approximation because we solve it using computers. But this is the part that the finite element method basically is or distincts itself from, let's say, something like finite difference method, because you approximate the equation you want to solve. And then this is happening basically because you do not solve your equation. So how can I write it? So in the finite element method, the differential equation that we start with, differential equation is transformed to something else, okay, to weak form. And then again, on that weak form, we have approximation, weak form. And then on that, you would have space approximation, which eventually means approximation of the equation. Okay, so this is the first thing that we will talk about. So this is that step that we go from, we go from strong to weak form. So you will see this soon, that the equation that we are going to solve is very different from a differential equation. As I mentioned, strong form is the differential equation that we start with. So this would be your differential equation. Weak form, funny enough, it's basically an integral. Okay. Or it's a differential equation, but again, the way we are going to write it, it looks like an integral, but in nature, that's a differential equation. But it's different, so it is weaker. It's actually called weak, right? So now that's the second type. So you have the third type of approximation, and that is, let's say, what I would call input approximation. In order to explain input approximation, I think an easy example would be this. Let's say we have a two-dimensional domain, a circle, and then we want to, I don't know, we want to apply some force or displacement to it, and we want to see how it's going to deform. And we want to do it using finite element method. So there is this thing that you need to discretize the domain. Basically, in finite element method, you need to split the domain into elements, and then you need to solve it. So if I want to do this, I have to use elements of the finite elements, and usually, let's say, we use triangles. They are very nice. But you can see if you use triangles, it's not easy to capture, let's say, what happens on the boundary. At some point, you have to make these approximations. Okay, so let's say this would look like a usual finite element mesh. Now, what you can see are these little pieces here. These are exactly the same type of, let's say, approximation that you would have when you want to, let's say, feed 45° or pi over 4 to an equation, because that thing by itself, it has approximation. So let's say even if you have the best approximation techniques for the first two parts, it still matters what you feed into your equation, what you feed into your problem, how you discretize your domain, okay? And this is, again, this is a question of the space that you use. So we call this space. But we have different, let's say, different versions of space. For simplicity, we usually use the same space for the equation, for the input, for the solution. And we will talk about that. But then, let's say, I naively, again, or brutally, I just call it space discretization. Okay. But as I mentioned, usually you also have different type of discretization. So if you need to discretize, and that's what we do. So for our discretization, you need to always ask yourself, am I discretizing, let's say, the domain? Am I discretizing the solution? Or am I discretizing or approximating? Maybe I just also say approximation here. What we will call later as test function. Okay, test for now. So let's say if the domain is something like X, the solution is something like displacement, maybe it's U, and the testing is something like W. So for now, they look sort of alien, these letters X, U, and W, but they will become clear in a few lectures, and we will play with them a lot to understand. All right, so that's really it for start. This is the roadmap of the finite element method. The first thing we need to do is to go from strong to weak form, but I wanted to also, before doing any of that, I wanted to show you this other one to show you that we have different approximations along the way, and they will add eventually to your approximate solution, and you need to be able to identify their sources and ideally, let's say, circumvent them as much as you can. So we start with a strong form then. Do you have any question? Good. So in order to just explain the strong form, or what we call maybe a differential equation, and in this case in 1D, I will remind you of a simple 1D example that we have also looked before, or looked at before, in maybe in ME 231, if you remember. So let's say you have, I don't know, a sort of cross section like this. So that's maybe this side. And this would be the other side. Okay. So this is sort of the cross section of that thing. If you look from the side, okay. So it's a one-dimensional problem. So you would have sort of x-axis here. Imagine this is your main axis, or symmetry axis in this case for simplicity. And then at each, let's say at each cross section, this thing has this area. So maybe I just draw a line here. So that line, let's say that straight line, is the area at X. Okay, so we are looking at something like a bar, let's say, but the bar is not exactly cylindrical. In this case, it has a change of or a variation of cross-sectional area. Okay, so again, I don't want to draw this, but think of it like this, if it makes you feel better. So it's like you're looking at this, and now the area here is a function of X. Okay, this is something like that, and this what the picture on top is just the 1D approximation of that. And we have done this a lot again before anyway. And the material, it's made of a material, and we assume that material has a, let's say, elastic modulus E, and assuming that the material property changes with coordinates for simplicity, well, or let's say for generality, we can assume that E is a function of X. Now, if I pick this little piece and I enlarge it, and then again, this is very similar to what we did in ME231 at some time ago. If I just do that little piece, you would get something like this. And say I want to write the equilibrium of forces on that. So on the right side, you have F plus dF. On the left side, you have F. That thing has, let's say, the thickness of dx. And maybe just again for generality, let's assume there is a body force density inside. Okay, so there is some sort of body force density, we call it B. Body force density. Now, body force density, again, it's a density of force inside the body. It's the name is on it. So density of force, let's say density of mass is mass per volume. Density of force is force per volume, okay? So this is force per volume. Or if you want to think about it, this is something like Newton per meter cubed. So maybe you can recognize it better if I multiply let me not do that. I want to tell you that you can recognize it if you think of it in terms of gravity. Okay, so let's go from the other direction. If you think of gravity, G, so you usually have this thing like mg equals F, right? So then you have force, which is Newton, is kilogram times G. So that G has the unit Newton per kilogram. Okay, so you can see that if you just sort of play with the dimension here, you get Newton per kilogram, kilogram per meter cubed, or volume. So you would get this thing that is usually your density, your rho, the mass density, and then you would have something that is looking like G, that's looking like gravity. Okay. So what I'm trying to say is that that body force density is basically something like the weight. But the usual way that you write it in terms of G, you usually think of it as per kilogram. So it's per mass. Here is per volume. That's the only difference. But I think thinking about gravity as a sort of body force or body force density, it's a healthy example if you are careful with the dimensions. All right, so let's say we have some sort of body force density, and then again, it could be of the nature of gravity or magnetic fields and so on. Now, if I want to write the equilibrium of forces on this picture, on the right-hand side, and assuming that, let's say this is my plus direction, okay? So I would have on the right-hand side, I have F plus dF. On the left-hand side, so this comes with a plus because it's in the same direction. Then you have this one, which comes with a minus now. And that body force density, it should have a direction. Again, if it is a, let's say, two-dimensional, three-dimensional example, this could have different directions. But for us, that body force density can only have one direction, okay? So it can only be horizontal. In other words, if you want to think of if you want to think of gravity, maybe you want to think of that picture that is somehow upside down, or it's turned. It is turned. Okay, that's okay if you do that. So you can just, let's say, equally assume that instead of having a, I don't know, a horizontal system, maybe I can have this system. It's perfectly fine to also assume this way, okay? And if you think about it that way now, you can see that your gravity, which is usually downwards, it's again in the same direction as X, so it's a good example. So it works if it is vertical. Okay, so that's that. And then again, as that force, that body force density, we need to multiply it by volume to make it a force. And the volume, again, if I call it dV, and the sum would be 0. Now that dV is this dV is the volume of this piece, and that would be the area times dx. So basically what we will have here, it would be df with respect to dx plus BA equals 0. And then again, now if you think of BA by itself, this looks like a force density per length. So it's like a one-dimensional force density. So if you think of that, this is like force density it's not per volume, it's per length now. So it has the dimension Newton per meter, for instance. So you may think of it as just a 1D force density. Okay, why am I emphasizing on a very simple example or trivial example like that so much? Because what you will see here, or the structure you see, would be exactly the same for 1D, would be the same for, let's say, formally, it's similar for 1D, 2D, 3D. It would be the same even for thermal problem, for electric problems, or magnetic fields and so on. So the story is the same story. And as I mentioned before, the story is something that mathematicians have started. So it is in terms of equations. It's not so much in terms of space dimensions and the physics or the mechanics of the problem. And the reason that I'm talking about it, let's say at this slow pace, is because it's very important. And then once you understand this, we can quickly adopt this and then adapt it to other dimensions or problems afterwards. All right, do you have any questions? Good. So I have 9:25. Let's have a 10-minute break. We will discuss at 9:30, or we start again at 9:35. Okay, so I'll talk to you in 10 minutes. All right, so now that we know the, let's say, this simplified version of mechanical equilibrium or balance of forces, we want to sort of particularize that for the type of problem that we are dealing with. So let's say we want to connect it to the concepts like stress, strain, and so on. Okay, so let me just do that now. So for a typical mechanical problem, or for a typical problem that we will be dealing with, or you know from, again, let's say mechanics and materials, force is stress times area. Okay, maybe I can actually shift everything a little bit up. So force is stress times area. We know that. We know stress is E epsilon in a one-dimensional problem. So E is your elastic modulus, epsilon is your strain, and then strain itself is du with respect to dx. Okay, so maybe you don't mind if I just call it u prime. It's a one-dimensional problem, so I think because we use 1D problem, we can easily use prime for the derivative. Okay, so that shouldn't be so difficult to follow. So if I just do exactly this thing again in the previous equation, basically what we have up there is d over dx of f. Now instead of f, I'm going to just insert what we had here for f. It would be d over dx sigma a plus ba is 0. And then instead of sigma, I'm going to write E epsilon. So it would be EA epsilon plus BA equals 0. And instead of epsilon, you write du over dx. So it's d over dx of EA du over dx plus BA equals 0. Okay, so this is your differential equation. Now, usually you can assume for simplicity that EA are constant. But this is, again, remember, this is the correct equation, what is in front of you. But if we make that assumption, so this is important that this is an assumption. So if you assume that E and A are just constant, you can take them out of the form that you have, and then A cancels out anyway. And that makes perfect sense because it's a one-dimensional problem. We expect, let's say, the area to disappear, which it does. So basically the equation you have is E u double prime plus B equals 0. Okay. So this is this is our differential equation. And as you can see, on top you have a picture, you have, let's say, a mechanical system. At the bottom, you have a differential equation. So that's the way we want to approach this problem. We want to think of it as a differential equation, not so much as a mechanical problem. Okay, so we are going to do that now. Let's say I'm going to remove these things. And then again, using what we just had here and the equation that we had before, now we know that the differential equation would be this. So if you put all of these together, you end up with this differential equation. Now, it's a second order differential equation. It's a linear differential equation. So maybe you want to just call it, I don't know, an ODE of second order. So ordinary differential equation of order 2 or of second order. So how many boundary conditions we need for this? We need 2 boundary conditions. Now, those 2 boundary conditions, they can be, well, they must be on the boundary. So they are either at 0 or at L, assuming that L is the length of the domain. So we need, and boundary means, let's say x equals 0 in this case and x equals L. Okay, so this is, L is the length of the domain. Now, if we just sort of think about a simpler problem and we want to play the same game with it. So what I'm going to do now is exactly as I mentioned before, I'm going to turn this problem. I'm going to turn it upside down. And we look at it as a one-dimensional problem, and let's say with something like gravity. Okay, so this is what we begin with. And as I mentioned here, the picture would be then a very simple beam. And then again, I don't want to give a lot of reference to our previous course on mechanics and materials, but since most of you had that course with me, you know I also talked about a very similar example when we had there. Let's say you have a bar that is hanging, and now you pick exactly the same bar, but you turn it upside down, okay? So now in the second case, it's basically carrying its own weight. Okay, so we have these 2 problems. We have a bar under its own weight. So now, depending on how you choose the coordinate system, you can define that parameter B, that body force density, which in this case is per length, but you can imagine this should be something like, or this should have something to do with, let's say, gravity. So for instance, if you think of these cases, let's say in the first case for the hanging bar, I am going to use this coordinate system. So I am going to assume that the coordinate system is downwards. And I do this intentionally, you don't have to change the coordinate system for a, let's say, for a hanging bar and a standing bar, right? You don't have to change the coordinate system. I do it intentionally to make it more interesting, to make them different, and to talk about more things, basically. So let's say this is a hanging bar. And this one, let's call it the standing bar. Now, for this one, I assume the coordinate system is here. And as I mentioned, this is just a luxury. I mean, for this problem, just as well, I could have assumed the coordinate system is here. Okay, this is perfectly fine if you use a different coordinate system, or you could assume it's in the center, and again, the direction is arbitrary. But what I want to talk about here, or what I want to emphasize here, is that let's say you have a domain and it has two ends. Okay, so it has two ends. Again, in this case, it would be 0 and L for us. But again, the ends are basically the boundaries. And it means on those boundaries, on those ends, you need to prescribe boundary condition, or the boundary condition at the end. So what would be the boundary condition? Now, if you remember, when we talked about springs, we talk about two types of boundary conditions. We talk about Dirichlet boundary conditions, and we talk about, let's say, Neumann type boundary conditions. Now we want to sort of use the same terminology or expand a similar view here. So remember, Dirichlet was somewhere that you apply displacement. Neumann was about force. Okay. So in view of these things, or what I have written here, and let me change the color of this to be consistent. Let's say, from this perspective, I want to look into these two bars and identify the boundary conditions. And now again, I emphasize that the differential equation you see here, it looks like we just have it for a bar, but it's a typical one-dimensional differential equation, and it happens in many interesting physics problems. Okay, so let's look at these two bars. And then again, if you think of the first case, the hanging bar, on top, it would be x equals, well, y equals 0 in this case. So this is y equals 0. So this is our top boundary. And then here you would have y equals L, let's say the length. So what are the boundary conditions? What is the condition that we have on top? What is the condition that we have at the bottom? And then imagine there is a gravity, right? So there is, let's say, a gravity of sort here. And the gravity is always downwards regardless of the coordinate system, obviously. Now, if you look at the upper part, you can see that the displacement is 0. Okay, so the change of, well, the domain or the bar is constrained on top. So there is no displacement on top. So u at 0 is 0. Now, we don't know how much force we have there. We don't know that. I mean, you may say, well, I know the area of this thing and I can calculate the weight and that would be the force, but that is the solution rather. That's not the condition. That's not a boundary condition. The condition you have is a Dirichlet type boundary condition, and it tells you that the displacement on top is 0. Okay. Now, at the bottom, on the other hand, we don't have exactly that information or that structure, but instead, we know that the derivative of the displacement is 0. Now, why is that? So if you think of any little piece of this, so if, I don't know, if you just cut a little piece here, you can imagine at this cross section, the weight of this whole part would be carried by whatever is on top of that cross section, right? So this part is going to carry the weight of the remaining part that is left underneath. Okay, so there is a change of length for every section. Their derivative of u would be a number. In fact, you can imagine that on top, although u itself is 0, the derivative of u is maximum. You can expect that because on top, you carry the whole weight of the structure. You carry the maximum weight of the structure, okay? So u prime is the change of u with respect to dx. So that means if you are here, if you are on top, you get the maximum change of u if you just move a little downwards. Whereas if you are almost at the bottom, so if you think of a cross section very close here, there is almost no weight underneath that is carrying that or that is pulling that. Okay, so the change of length per dx is very small. So again, at the bottom, you have the derivative is 0. And then again, having this derivative 0 is very much similar to having a force 0. So you can think of it this way, that here on top, you would have so much force applied on that point to carry the whole weight. So that is that. And then here, basically, there is no gravity. So if you are just at this end, at the end point, there is no additional weight underneath to pull it. So the force is 0. Okay, so let's say, long story short, the displacement types are Dirichlet type. They are easy, and they basically just easily translate to u. So if you have a prescribed u, it means you have a prescribed displacement, and it's a Dirichlet type. If you have a prescribed force, or let's say if you have no force, in this case, it would be u prime is 0. But if you have a prescribed force, you can also relate that to u prime. Okay, so it's how it works basically. And then again, I just remind you that, remember that force in general. So if you want to think of a force, F is sigma A. Sigma is E epsilon. Epsilon is u prime. Okay, so you can clearly see the connection between u prime and F. In other words, if there is no force, there is no u prime. F0 means u prime is 0. And then if you have a prescribed F, then that prescribed F divided by EA, that would be your u prime. All right, so anyway, long story short, if you have a differential equation like this, you have two ends, and at each end you can have either Dirichlet or Neumann type boundary condition. And if you look at the right picture, obviously you have the opposite of what we just had for the left picture. So here for the right picture now, y equals L would be on top, and then y equals 0 would be at the bottom. And in terms of boundary conditions, you can see that here now on top, so u prime at L would be 0 on the right picture, and here u at 0 would be 0. Okay, so basically the boundary conditions, they look similar because we changed the coordinate system, we rotated the coordinate system. We could have kept the coordinate system constant and then the boundary conditions would have changed. But this is basically the game that we play. So these two, you can see they are essentially the same type of boundary conditions, and these two are the same type of boundary conditions. The only thing is that in this system, G, it has the same direction as the coordinate system, so it enters as a plus G into your equation, and eventually it results in elongation. In this system, G has the different direction or opposite direction to your coordinate system, so it enters as minus G into your differential equation, and eventually it results in compression of the domain, which makes perfect sense. So, and basically you can imagine that the, let's say, a standing bar would be compressed, and the hanging bar would be, let's say, elongated, or it undergoes elongation. Okay, so this is what we can expect from the two examples. If I also want to go one step further and draw the, let's say, the diagrams for this, I can do that. But maybe before that, we can or we should solve this. Okay, so that's what we want to do now. We want to solve this very, very simple example for the two cases. Again, for the case, let's call this maybe case 1, and that is the hanging beam, and let's maybe call this one case 2, and that's the standing beam. Okay, so I will write it first for the hanging beam. So case 1, hanging beam. We want to solve that together and see what we get for the solution of the system. So the differential equation, as I mentioned, is just what we have up there is EU double prime plus B equals 0. So the differential equation is identical. This is important. Now, what is B in this case? B is rho G. Okay. So this is basically gravity times density, if you want. Okay. Very good. So if you do that, then just writing the differential equation and the boundary conditions, we would have this one. We would have EU double prime plus rho G is 0. And then again, as I mentioned before, G comes with a plus sign because it has the same direction as the coordinate system itself. And the boundary conditions are, we usually like to write it like this, subject to boundary conditions. And in this case, the boundary conditions are U at 0 is 0 and U prime at L is 0. And this is a second order differential equation. You can easily integrate it twice. Then you insert the boundary conditions and you can calculate the constant. So that's what you want to do next. So basically, what we will do is to just integrate this twice and insert the boundary conditions. Okay, so if you integrate this twice, you get this. You get U equals minus 1 over 2 rho G divided by E y squared plus C1y plus C2. And if you use the boundary condition, if you insert the boundary conditions, so here is where the boundary conditions enter the system, you would get something which looks like U equals minus 1 over 2 rho G divided by E y squared plus, let's say, rho G L divided by E y. This would be the solution to your problem. Now, a very simple check here is that, for instance, if you want to test your boundary conditions in it, you should be able to do that. So you can see that here at 0, you get actually U is 0. At L, U prime would be 0. But also now, since we have that, we can actually calculate U at L. So at L, UL would be 1 over 2. Let me just make a little more space. It would be 1 over 2 rho G divided by E L squared. Okay. So as you can see at L, at the bottom, you get a positive displacement, positive value for U, which means elongation. So that's the first case. Remember, for hanging beam, then we have this differential equation, and then it satisfies the boundary conditions. Now, we are going to quickly do the same game for the standing beam, or standing bar in this case. So maybe I use the word bar instead of beam for, for just being too precise. Okay, so if you want to do that, and we are in the next page, it's in the standing bar, very little or very few things are changing. So this thing becomes a standing bar instead of hanging bar. And then in the differential equation, you get a minus here. You get a minus here. So that means all you need to do is to change this to a minus. And then you get a plus here. So a minus here, a plus here instead. The boundary conditions, again, surprisingly, they don't change, but they already correspond to a different coordinate system. So it's okay if they don't change. Let's say visually they don't change, because fundamentally they actually are very different now. And if you do that, you end up with this differential equation that looks like basically the same thing with opposite signs. So now you get a plus on the first term, and you get a minus on the second term. And this is very clear again. Now, if you play the same game that we played before, at 0 you see that you have 0 displacement, and then at L you have now minus 1 over 2 rho g L squared divided by E. Okay, so basically you can clearly see that you get the maximum displacement at L, which makes sense. On top, you get the maximum displacement. At the bottom, you get 0 displacement. But on top, you get 0 derivative of displacement. At the bottom, you get the maximum derivative of displacement. So they have this sort of opposite directions, you know, the displacement and its derivative for this particular problem. Okay, so now that we have the solution for both of them, I want to also just, let's say, quickly summarize this into one slide. So let's say if we do the hanging bar, you get this. So for the first problem, we get this solution. That's your hanging bar. And then for the second one, for the standing bar, I'm just going to copy paste the same thing and only change the signs accordingly. Okay, so this would be minus, this would be plus, this would be standing. All right, so the next thing we want to do, and basically the last thing we want to do regarding this example, is to plot them and see how these graphs are looking like. So in order to do that, I'm going to even clean up this slide a little more to make even more space. But you just know at this point that if it's a hanging bar, you have that problem. If it's a standing bar, you have this one. Okay. Now let's draw this. Or plot the graphs. In order to do that, I will just plot let's say u with respect to y. And again, because we used the coordinate system such that they both start from 0 and they go to y, we would get similar graphs in a sense. But then in order to make the story more clear, I'm going to do something a little strange here. I'm going to turn the second graph upside down to highlight that one of them is basically elongating and the other one is compressing. So let's say this is one of the graphs for system 1. Then I duplicate this and I turn it, if I manage that to do that. Let me just redraw it. It's not what I want. Okay. So the right system is for the right bar, for the standing bar, and then the left one is for the hanging. So this would be now your y, and this would be your u. Now in the left system, the graph would look like, let's say this is system 1, and this is system 2 for the graph. Here your maximum u, remember the maximum u happens at the end, at u equals L. Sorry, at y equals L. So you get your maximum displacement here. Let's say this is L. And this would be your U max, which we calculated before. The graph will be, or the solution would be something like this. It's a quadratic curve. I'm going to also exaggerate a little to make the points more clear. So it would be something like this. Now, what you can see here is that here you get the maximum U, but also what you see is that U prime would be 0. At the beginning, what you see is exactly the opposite. Here you see U is 0 itself, but you see the U prime is maximum. Okay, so this would be your U as a function of Y, and this would be the analytical solution. So this is exactly the, let's say, the green solution that we have here. Let's call it star. And then again, the reason I'm emphasizing so much on this very, very simple example is that we keep solving this using different approximations and using the finite element method in the following lectures. So it's very important that you have a good feeling of this graph, of the results, and what, or the steps that we have done. So again, the game here is that if you have U prime max, it means you have maximum force. And when you have U prime 0, it means, or if U prime is 0, it means no force. Okay. We can do the same thing for the right graph. So that's what I'm going to do now. Again, let's say here you would get the maximum u at the distance L. But now I want to do it downwards, or to kind of identify that it is, you know, it's a negative value. So here, if you plot it, you see a similar story, but now kind of upside down or rotated. It's again a quadratic function, which you know the derivative here is 0 at y equals L, and then the derivative is maximum when it comes to the beginning. So something like that. And then again, to be clear, maybe I don't draw exactly the, you know, the arrow for u, so that you know it's still u is upward. So again, this means just a minus sign. So maybe I just, it's still the u component, but to be clear that this is now negative. I'm plotting it like that. Okay, so now the value you have here is now u max. Although again, in this case, I emphasize that u max in the second case, let's call it double star. This is the double star solution, the graph that we are plotting here. And if you remember, at y0, sorry, at yl, you get u max, but it has a negative sign, so it has a negative value. So I just make it clear, this is negative, this is positive, but they are the same number. And the same story holds. So you can see again that at the beginning here, u is 0, u prime is max. So u prime is the derivative of the function. So it's the slope of the line. You can see it gets the maximum slope. And then at the end, well, it's the opposite. So u prime is 0 and u is max. All right. So long story short, this is what we did, and that's exactly what I wanted to end this lecture, and that's what we start with we start from in the next lecture. We showed that this is the differential equation for a one-dimensional system to let's say to govern the equations, or it's our governing equation, and it's subject to boundary conditions. And we talked about boundary conditions. Again, you get, let's say, Neumann type boundary condition and Dirichlet type boundary condition. Now, we made a simplification assuming that E and A are constant. And if E and A are constant, we can write that equation as, let's say, EA U double prime plus B A equals 0. Now, the next thing is that you can also cancel A, which makes sense because it's a one-dimensional problem. You may have a good feeling that A should not do much. And you can also write it as just U double prime plus, let's say, f equals 0, where f is defined as b over e. Okay, so this is sort of the ratio of your internal force divided by the elasticity of the material. For simplicity, we are also going to assume that the domain has a length of 1 from now on. So we assume that we are going to solve it over a domain of length of 1, and this is the differential equation we want to solve. And then also, for simplicity, we assume the boundary conditions are, for instance, of the following type. Let's say at u0, let's say we know what is the value of the displacement at 0, and then at the end, which is 1, we know the value of the derivative. Okay, and then let's call it t. All right, so these two boundary conditions are very similar to what we had just up here. So we say at the beginning we know what is the displacement itself. At the end we know what is the derivative of displacement. So this is a very famous set of differential equation. You may also think of it as, let's say, Poisson equation. And as I mentioned, this appears in almost every physics problem. So it doesn't have to be exactly mechanic. If it's a thermal problem, it's a similar thing. So what we want to do next, or in the next lecture, is to start from here. So this thing, this differential equation, is what we call a strong form. Okay, so we start from this. We have a differential equation with given boundary conditions, and we want to solve that approximately using the finite element method. This is what we want to do. And if you remember, I come back to our roadmap, that's what we said. So today we wanted to identify what's the strong form. What we want to do next is to go from a strong form to weak form. And then after many steps, we get to the solution of this differential equation. Now, for this equation in particular, as you can see, or as you saw the previous problem, it's very simple. We know the analytical solution already, but that helps us to better understand what is going on and to compare with the, let's say, with the approximate solution. So it's a very interesting and a nice benchmark, while it is also a very generic mechanical differential equation. So it's a very useful equation. Very good. Do you have any question?
I missed that part, sir. What was the t? Can you say it again?
T is just the derivative at 1. Again, it depends on your problem. Here, for instance, it was 0.
Okay.
It's if you, let's say, if you think of the same beam, but now imagine you have a weight hanging at the end. Okay, or if somebody is pulling it. Okay, it's just a prescribed value. So thank you for the question. That's a good question, actually. So these are prescribed. Okay.
Okay, thank you.
These are values that maybe, yeah, I think P is okay. Yeah, it's a number. Let's say it's 510 something. So the point being that the first one is more Dirichlet type boundary condition, and the second one is more like a Neumann type boundary condition. Thank you very much. All right. Have a good day, have a good weekend, and I will see you next week. On Tuesday, we have a quiz, and then we continue with the lecture on Friday.